So let's consider metallic bonding. Now, it's a very simplistic model that we can have of metallic bonding, but it can be quite effective. It can explain some of the properties of metals. Now, metals, of course, are crystalline, so we know that we have a lattice structure. It's a giant metallic lattice structure. So we've got, in our description, a lattice of metal ions. Of course, metals tend to lose electrons, so those will be cations, and they'll be sitting in a sea of electrons, or a sea of delocalized electron density. So if we have sodium, for example, it's got electron configuration, as you can see there, 3s1, and it will tend to lose that one electron to the sea of electron density, and it's that sea of electron density, a negatively charged electron density, of course, which will attract the cations. So we get the electron density acting, if you like, as a glue between the cations. The cations will be attracted in all directions towards the negative charge, and the only thing that stops them moving in constantly in one direction, of course, is the repulsion, the balance of repulsive forces between the cations once they get a little bit closer to each other. If we were to consider magnesium next door to sodium, that would be 3s2. Now that can lose 2 electrons to the outer shell, to the sea of electron density. Now that therefore means that we have a much smaller cation, we have a greater electron charge density in the sea of electron density, and therefore we're going to have much greater electrostatic attraction between the cations and the sea of electron density surrounding them. Therefore we will see a change in properties. We'll find that the melting point of magnesium will be much higher than that of sodium. Magnesium will be harder than sodium as well. Another slightly more sophisticated model of metallic bonding is to consider the overlap of the s orbitals of the sodium, for example. And if one overlaps the 3s orbitals, this enables those 3s electrons to become mobile. They're able to move freely through the lattice structure. The consequence of the mobility of those electrons means that if you put a potential difference across the metal, those electrons can move. And therefore we produce electrical conductivity for metals. Now, I've talked about the electrostatic attraction of the cations for the electron density between them, and this produces generally strong metallic bonds. Metals tend to have high melting points and boiling points. Exceptions to the rules, for example, mercury is a liquid, sodium, of course, and a lot of the group 1 metals have very low melting points. Cesium melts in the hand, for example. I wouldn't put it in your hand if I were you. But a lot of these metals also have another consequence, and that is malleability. Now, malleability is about the beating into shape, and we can do this without breaking the metallic bonds. If, for example, we were to try to do this with a giant ionic structure, it would shatter. And the reason for that is that the electrostatic attraction in an ionic structure is between the lattice of cations and the lattice of anions, oppositely charged ions next to each other. Now, if we hit that with a certain amount of force, we will be able to move the lattice structure along the cleavage plane. And the effect of that movement of that lattice structure only by a few nanometers would be enable the cations to move next to other cations, and anions moving next to other anions. And of course, instead of attraction there, immediately we get repulsion, and the crystal structure will fall apart along that cleavage plane. But with metals, it's slightly different. because we can see that in this particular case, whilst we move the crystal structure down, the electron density still remains between the cations. The cations are only getting slightly closer to each other, if at all. We still have that mutual attraction for the electron density between them. And that therefore means that the metals will not break in terms of crystal structure. But of course, this again is a simplification, because some metals are brittle, but that is partly at least due to the size of the crystals that exist there.